Welcome to Spectroscopy video number 1. PowerPoint 11.3a 21.1a. Intro to Spectroscopy. Well, okay, no. Spectroscopy video 1. Here we go. In terms of accessing prior knowledge, there are some things that will be helpful. Stoichiometry, kind of just remembering mole ratios for equations, chemical structures and organic nomenclature, mass spectroscopy. From topic 2, we studied it a little bit, empirical and molecular formula determination, and the electromagnetic spectrum from topic 2 as well. This is actually combo standard level, higher level material, all the kind of the sequencing of spectroscopy together. And spectroscopy is really about an analytical technique or a series of analytical techniques that can determine structures, composition, quantities. And so I'm not going to read these big ideas to you because we'll kind of access them over the course of the next 5 videos. First of all, just a little bit of an overview. 3 kinds of analysis that we can look at. Qualitative analysis is simply determining the presence of a substance. Quantitative analysis is determining the quantity of a particular substance in a mixture. And structural analysis is trying to determine how things are arranged in space in terms of a molecular or crystal structure. And this particular section will focus on structural analysis. Spectroscopy will focus on determining structures of unknown compounds. 3 main kinds of spectroscopy that we will study, although there are numerous other forms of spectroscopy as well. We will study infrared spectroscopy, mass spectrometry, or mass spectroscopy, and NMR, nuclear magnetic resonance spectroscopy. We'll also just very briefly study something called X-ray diffraction, which is we're just going to touch the surface of X-ray diffraction, really. So in order to understand a little bit about what we're going to talk about in spectroscopy, we need to review the electromagnetic spectrum. However, the real operating principles of these forms of spectroscopy are not required, but just a little bit of background. Electromagnetic spectrum is given in your data booklet. This section down here comes from your data booklet, and here's sort of a list from your textbook just reminding you from radio waves to microwaves to IR to visible, ultraviolet, X-rays, and gamma rays. The energy as you go from radio waves to gamma rays, the energy is increasing and the wavelength is decreasing. Visible spectrum is kind of right in the middle here between ultraviolet and infrared. So, radio waves can be absorbed by certain nuclei, causing them to reverse their spin. And this is, okay, now we're talking about something that's a bit new. Details, again, of the operating principles are not required, just a little bit of background. These radio waves can be used in NMR and can give information about the chemical environment of certain atoms. We'll focus on hydrogen. Microwaves cause molecules to increase their rotational energy, and this can give information about bond length. We're not going to focus on microwaves too much. Infrared radiation can be absorbed by certain bonds, causing them to stretch or bend, and this can give information about the bonds. We will learn about infrared spectroscopy in a couple videos down the road. Visible and ultraviolet light can produce electronic transitions and give information about electronic energy levels. We do a little bit of UV visible spectroscopy studying Beer's law. We're not going to focus on that in this section, but it's just a little bit of a reminder. And then X-rays can be used to produce diffraction patterns which provide direct evidence of the molecular and crystal structure. So we've talked about a few different forms of radiation and the relationship to the spectroscopy. Radio waves for NMR, infrared radiation for IR, and X-rays for X-ray diffraction. Now, it's a not spectroscopy specifically, but something that will be related to structural determination is called the index of hydrogen deficiency. Unfortunately, the formula for IHD is not in the data booklet, so it's something we have to memorize on some level. So the index of hydrogen deficiency is basically a measure of how many molecules of hydrogen would be needed, in theory, to convert the molecule that we're studying, whatever molecule we're looking at, to the corresponding saturated non-cyclic molecule. Saturated, all single bonds, non-cyclic, not forming a ring of some sort. And here's the formula. Now I can write this a couple different ways. I've got this sort of generic chemical formula here with the little subscripts N and P and Q and R and S. I've also seen the IHD formula written in this form. 2 times carbon plus 2 minus hydrogen minus halogens. X stands for halogens. And so let's label that here. Plus R, where R is nitrogen. All divided by 2. That is another way to write the formula, using capital letters here to represent elements that are part of a formula. Notice that oxygen might be in an organic compound formula, but it's not part of this formula. We'll talk about that a little bit later and why that is. So let's do a couple examples. Let's do cyclohexane and hex-2-ene. Draw those structures. Pause the video, draw the structures, a little bit of practice. And here are the structures. Cyclo means ring structure. Hexane, ane means they're all single bonds. But that has a formula, C6H12, so it seems to be missing some hydrogens because it really should be C6H14 if it were completely saturated as a straight chain, 1, 2, 3, 4, 5, 6 carbons. If I put all the hydrogens around here, I would get 14 hydrogens. So even though this is all single bonds, it's actually missing some hydrogens, so to speak. We still call it saturated, but it is missing 2 hydrogens. Hex-2-ene has a double bond between the second and third carbon. So let's calculate the index of hydrogen deficiency for these 2 molecules. They both have the same formula, C6H12. So we can actually calculate the IHD for both compounds. So, sorry about that. Wrong kind of pencil. 2 times the number of carbons, which is 6, plus 2 from the formula, minus P, which is the number of hydrogens, so minus 12, minus S, which is the number of halogens, which is 0, plus R, which is the number of nitrogens, which is 0, all divided by 2, or times a half, however you would like to manipulate that. So I have 12 plus 2 minus 12 divided by 2. That equals 2 divided by 2, which is 1. So these 2 compounds have an index of hydrogen deficiency of 1, which means that they are missing 1 H2, or if I were to have a reaction of hex-2-ene with hydrogen to make the fully saturated compound that had all the hydrogens in a linear chain or in a non-cyclic chain, I would need to add 1 H2 molecule. Kind of means there's 1 double bond, or it means there is 1 ring. Every unit of index of hydrogen deficiency means 1 double bond or 1 ring. Sorry about that, a little cough. Every unit of index of hydrogen deficiency means 1 double bond or 1 ring structure. So if I had an index of hydrogen deficiency of 2, it could be 1 ring and a double bond within the ring. It could be 2 double bonds in a structure like this. So let's take another example. Mildronate is the drug that Maria Sharapova was suspended for in tennis as a performance-enhancing drug. And it has formula C6H14N2O2. Calculate the index of hydrogen deficiency using that formula, and then we'll talk about it. Okay, so remember your formula. 2 times the number of carbons plus 2 minus hydrogen minus halogens, which we don't have, plus nitrogens, all divided by 2. So here's the work done. I did 1/2 in this equation. 2 times the number of carbons is 6, plus 2 from the formula, minus 14 for the number of hydrogens, minus 0 for the number of halogens because there were none, plus 2 for the number of nitrogens. All of this math together gives us an index of hydrogen deficiency of 1. Now this is the structure of mildronate. A little bit interesting. It's called a Zwitterion, where you have a negative charge on one side and a positive charge on the other side of the molecule, but overall this is a neutral molecule. Why is the index of hydrogen deficiency 1? Let's focus on where that would come from. So we have a double bond here. That double bond reduces the number of hydrogens that can be part of this molecule. If this were a single bond, we have this oxygen here, I would have an oxygen and a hydrogen, and then this would probably have a hydrogen on it, ignoring the fact that this is a little bit odd with an ion here. So by having this double bond, it removed 2 hydrogen atoms from the overall structure. So that's why the index of hydrogen deficiency is 1. The presence of oxygen doesn't necessarily have to remove hydrogens, because if I have an alcohol, if I think about the hydrogen that's attached to the alcohol could be just attached to the carbon. So the presence of oxygen alone does not cause a double bond, and that's why oxygen is not part of this formula. The presence of oxygen does not influence the number of hydrogens directly, only if there's a double bond. Nitrogen, however, adds a hydrogen. So this nitrogen has an extra hydrogen here. If this were oxygen, COC, like an ether, there are no extra hydrogens there. So nitrogen is plus in terms of just trying to understand the formula. How will this be helpful? I think we'll see down the road how it will be helpful when we look at determining structures from spectroscopy and figuring out how many double bonds or rings might be part of a structure. So there is a context. It seems a bit out of place now, but there is a context. Now we're just going to briefly talk about something called X-ray crystallography. This is a bit of an intro. Next video we'll talk about mass spectroscopy with more detail. X-ray crystallography can be used to identify the bond lengths and bond angles of crystalline compounds, and the key here is crystal compounds. X-ray crystallography. In short, in brief summary, X-rays are blasted towards a crystal, and that diffraction pattern is recorded, and some math that is way above my understanding is completed in order to determine the structure. Essentially, it has to do with interference between the X-rays as they bounce off the atoms and are diffracted, constructive interference between 2 waves makes one bigger wave, and destructive interference makes essentially no wave. Brief overview, a little bit of physics going on here. And so when the X-rays are shined onto the object, the atoms diffract the X-rays, and because of the wavelength of the X-rays and the distance between the atoms, the X-rays are diffracted, and this diffraction pattern can be calculated and give a structure. Here's a simple diagram. Crystal shining X-rays through it. You get a scattering pattern. And Rosalind Franklin, this is worked on the diffraction, X-ray diffraction of DNA, and helped actually Watson and Crick determine the structure, although she wasn't given a whole lot of credit for her work. 1953 when that happened. So this is an X-ray diffraction from her work in 1953. How can you take this and make the double helix of DNA? Well, I have no idea. I'm just telling you honestly, this is above my understanding. But what do we need to understand? Well, modern X-ray diffraction might give something like this, where after calculations, we can see the presence of atoms and electrons, if you will, here in a structure. So this diagram is the result of the calculations of the X-ray crystallography for a particular compound. And the compound would be anthracene, which would look like this. Now, it may be a little bit of a leap to make this determination. I mean, if I look at this as a hexagon, these are all hexagons. That's pretty easy to see. Hydrogens don't give much of a signal on X-ray diffraction. They're very small. How could we know that these are benzene rings, if you will, with some conjugated double bonds? Well, that would be difficult to determine. But that's not the key, if you will. The key here is, can I use X-ray diffraction on some level to understand something about a molecule? I'm going to remind you of the guidance from the syllabus. The precise details of single crystal X-ray crystallography need not be known in detail, but students should be aware of the existence of this structural technique in the wider context of structural identification of both inorganic and organic compounds. So what will you have to know about X-ray diffraction? Not very much. Just that be aware of it as a technique. Understand that it's used for bond angles. We could determine an angle from this. We could determine a bond length from this. And it helps in structural determination. And I think X-ray diffraction is something that makes more sense later after we've done more work on spectroscopy. Not that we understand it better, but it gives it a little bit better context. International mindedness. Monitoring analysis of toxins and xenobiotics in the environment is a continuous endeavor that involves collaboration between scientists in different countries. I bet you didn't know that. TLK. Electromagnetic waves can transmit information beyond that of our sense perceptions, like X-ray diffraction. What are the limitations of sense perception as a way of knowing? In terms of relationship to other topics, IR spectroscopy is used in heat sensors. Protons in water molecules within human cells can be detected by MRI, giving a three-dimensional view of organs in the human body. If you've ever had an injury of some sort, you might have received an MRI. MRI is called magnetic resonance imaging, although it's related to nuclear magnetic resonance. And a bit of a marketing scheme here, instead of calling it NMR, nuclear magnetic resonance, they call it magnetic resonance imaging, so that the public doesn't think it's some nuclear thing, because it's not. The word nucleus just means, nuclear means nucleus. It doesn't mean nuclear like nuclear energy. Topic 1.2, empirical formula. We'll look at this more down the road. This is a bit of an overview of what spectroscopy can do. As a summary, today was really just an overview. We'll do more details in the upcoming videos. Analytical and structural analysis can be a very useful tool for chemists. IHD can provide information about the structure of a compound. We will learn more about this in the next video, but mass spectroscopy fragment patterns, which we didn't really mention in this video, but because this is an overview, I left the summary of everything here. Mass spec fragment patterns can be used to help deduce chemical structures. As I said, coming up in the next video. A little preview. X-ray diffraction patterns can lead to chemical structures as well. And so this summary point, not very detailed, kind of on purpose. And that is the end of this particular video. Thank you for listening. There are no checkpoint questions for this video, and so you're certainly not required to fill out the feedback form. But if you want to ask a question or provide feedback on the video, you are welcome to do so. And the video title will be Spectroscopy Introduction. Thanks again. See you in class.